We are Crimmins Renewable Energy Distribution System, sponsored by Roger Crimmins. Our senior design project consisted of creating a solar field feasibility study with a given brownfield site. In order for this project to be successful, the work included designing a physical solar field, component research and recommendations, creating a protection scheme for the existing substation connections, as well as a thorough economic model to propose to our sponsor. Throughout this process, work was done in collaboration with the alternative energy enterprise. Solar power. It's one of the most popular renewable energy generation methods in the world. From small residential applications to large utility scale solar fields, energy is harnessed, then distributed to the grid. From keeping the production line moving to turning the lights on in your house, solar is one of the many methods for generating green energy. In order to complete this project, we divided into two teams, a solar team and a distribution team, each one committed to different tasks. The location of this project is in the beautiful area of Marquette, Michigan, stretching along the shores of Lake Superior and just north of downtown near the active ore dock resides our site. This was previously the home for the Presque Isle power plant, which was completely demolished a couple years ago. Now that we understand the location of the site, there are constraints associated with it, some of those being rough terrain, limestone storage, and existing infrastructure. Based on these limitations, research was conducted in order to select the most appropriate components for the project. In our selection process, we had to choose a solar panel, mounting types, and an inverter. The selected solar components are the Trina Solar 720-watt panel, which is a monocrystalline bifacial model, a Schletter fixed mount, and an Array Duratrack single-axis tracking mount, along with an SMA Sunny Tri-Power 30 kilowatt inverter. The energy being harnessed by the solar components will then be distributed onto the grid. In order to achieve that, the selection of distribution equipment will be required. The equipment selected will be the step-up transformers, fuses, combiner boxes, and a battery energy storage system. After comprehensive research, the distribution components that were selected are a step-up transformer of 480 volts to 12.47 kilovolts and another step-up transformer of 12.47 kilovolts to 69 kilovolts, which is the local voltage level. In addition to that, combiner boxes as well as 3,500 amp three-phase fuses were chosen for system protection, and a battery energy storage system was selected to collect power over time. With all of the solar and distribution components selected, two simulation softwares were used in conjunction, the first being Helioscope to generate important parameters such as the number of panels and inverters along with potential energy outputs. The second simulation software being System Advisor Model to generate system performance data and finance calculations. Using Helioscope, we generated a physical layout that was approximately 17 acres in size. Then the amount of solar panels, inverters, and estimated power and energy outputs was calculated based on the aforementioned layout. Using the data collected from Helioscope, System Advisor Model was then used to generate potential payback periods. Factoring in different rates of electricity, government incentives, and different mounting types, the projected length of time it would take to pay off our investments was calculated. To cross-reference the data collected from System Advisor Model, a financial model was developed. Adding together capital expenditures and operational expenditures, then subtracting potential government incentives gives us our investment. That investment is then divided by the projected energy returns, resulting in a payback period. A graph was developed to demonstrate the payback period. Accounting for government incentives and using a single-axis tilt mounting system, a payback period was also calculated to be approximately 11 years. The recommendation to our sponsor is to move forward with 720-watt solar panels, which will be mounted using a single-axis tracking system in conjunction with 30 kilowatt string inverter. Those solar components will feed into our distribution system, which we recommend using two step-up transformers to get up to the local voltage level, fuse protection, and a battery energy storage system. For future considerations, if another team is wishing to move forward with this project, they should inquire about specific substation information, perform an interconnection study, research power purchase agreements, soil resistivity and testing, grounding, and acquire government subsidies and incentives.